Hello, and welcome to another episode of Scaling Robotics. Scaling Robotics is a series of conversations with leaders in the robotics industry about their journeys and experiences and lessons scaling fleets of robots. And the goal is to democratize some of these learnings to help the next generations of robotics companies scale better and faster. Today, we have an awesome guest. I'm here with Ash, CEO and founder of TorqueAGI. Ash, thanks so much for joining us. Do you mind introducing yourself?
Yeah, I am Ashutosh Saxena, go by Ash. I am the founder and CEO of TorqueAGI. Previously, I did my PhD with Andrew Ng in the area of developing AI for robots, built a company that went public called Catapult, and super excited about building foundation models for robots today.
Thanks for being here. Do you mind sharing a bit more about TorqueAGI? What do you guys do? Any stats about deployments or customers would be awesome to give our viewers some context about you and your company.
At TorqueAGI, we develop foundation models for enterprise robots. So these are large scale models, learn from different embodiments of robots, all the way from commercial tractors to mobile manipulators to construction robots to humanoids. And because it's the same model, learning and building for a variety of these different robots, it improves over time. And one of the emphasis that we do for in our company is really focus on the edge cases. So when robots go into the field, into the real world variations, that's where intelligence really matters. Not just mapping a toy problem, a demo problem, but our customers work with us when they are into the field for millions of data points, tens of thousands of hours of data. That's when the AI is really needed.
We think about autonomy, in the real world. We've obviously seen so many demos from different labs on social media, but when you think about delivering real autonomy, production grade autonomy, what are the big gaps between what we see in demos and production? What are the things that people focus too much in the lab and not enough in the field within, autonomy?
Building one demo which may be solving a difficult problem does not equal intelligence or does not equal autonomy, in my mind at least, right? And for most roboticists. And let's take the example of a self-driving car like Waymo, right? The demonstration of driving it once existed back in 2005 before something called a DARPA Grand Challenge was even started. You had demonstrations of a car or a shuttle going from point A to point B, and there were very good researchers demonstrating that. But after that, it took almost 15 to 20 years to get to a point where you can actually drive a car in the real world. The AI is really tested when it meets the reality, and most AI fails. And these edge cases vary across different robots. So going from self-driving cars like Waymo, let's talk about commercial tractors as an example. To make a tractor go from point A to point B is okay. But when the tractor is actually performing the work, it has to deal with animals roaming around, a electrical pole that might come out of nowhere. These are all real-world edge cases that the robot must be aware of. Now, going even further to humanoids, we have seen some of the demos about the humanoid picking up one object and placing it in another. But I've never seen an apartment that clean before in the real world. Like my apartment used to be very messy. I don't think the robot can handle that edge case.
When we think about, reliability and making these things production grade, um, what are the tactical things that you're doing to ensure that your model is ready for production, that it's able to reach certain nines of reliability? And do you have any tips that you can share, with other folks on how they just might do that?
That's a very good question because when we build AI for production, we have to make sure that it is designed for production in the first place. A production, interpretability, reliability shouldn't come as an afterthought. So, number one, we need to have what we have done is we have designed interpretable agents that query the model or harness the model in a very interpretable manner that lets the designers of the robotic system see the intermediate outputs along the way. And that's a very powerful way of making sure that parts of the system pass the test. System can be end-to-end. It has to function fully. Everything has to be referring to the same matrices, the same tensors. However, we need to be able to have unit tests on components because there's industry requirements in some of the cases. So That's part number one. Part number two is we have to ensure that those models meet the performance standard. So what the AI models are really good at is creating a soft ranking or guesses on things. That was the case on previous generation AI when it was giving probabilistic outputs. And that is the case today when it is giving probabilistic outputs. Every time you ask the question, it will be a variation. It's very hard to get it to get to 99.999%. So the way we have designed our model is that we have taken the AI traditional models and combined that with physics informed approaches. So now models have access to data driven knowledge, but also physics driven knowledge that it has learned. So a very simple example is, let's take the case of a very simple yes no answer. Can I pick up a object on the top of a table? If the object is beyond the reachability area of the arm, it is just further away than the total length of the arm, you just can't pick it up, right? So you do not need the model to reason millions of samples inside it to come up with that answer. Model can cut short its thinking and say, oh, now I know the kinematics of the arm and its reachability, so I need to reason with that in mind. Now, suddenly with combining those two approaches, what happens is you are getting that 99.99% grounding in reality along with the power of the AI. So those two things combined together, interpretability through agents and reasoning with physics, is allowing our models to get to production faster.
You guys are working with, some huge enterprise companies, Fortune 100 customers like John Deere with, tractors, and then Canvas and construction. I'm curious to hear a bit more about the value that you deliver for those customers, why the models are so effective, and also why you mentioned that, learning from both of those different, seemingly unconnected industries is actually more useful overall for the AI models and what they're able to do and with their physical reasoning.
So typically, think of a company like John Deere that we are working with. Um, such companies have typically 10 different models of tractors. And for the way of background, a tractor is a mobile robot. Uh, it can move around. It has some articulation because you can have implements behind it. So it can help it pick up items, place it, dig dirt, or do numerous agricultural items from removing weed, crop, and so on and so forth. So that's on the action side. On the sensing side, it has a very similar setup like any other robot. It has a suite of sensors. It has robot telemetry, often has access to a noisy GPS, and very often on all the cases we work with has access to a set of cameras or LiDAR-like sensors. Uh, Now, the challenge is that we have to address when solving this kind of autonomy is there are many use cases in the agriculture. So one is a very common use case, which is, hey, go from point A to point B and do not hit any obstacle, do not fall into the ditch. So that's a mobility use case. The second use case that you can think about are use cases where you have to do certain things, like identify uh, weeds that grow up from the crops, and there's a huge food wastage. And a completely second use case is drywall. When you are trying to make a very smooth drywall, so think of a wall in which you have to paint, you have to figure out what spots are rough or not painted, and otherwise figure out which spots to paint. Now, these are entirely two different use cases, but not for AI. The AI can actually reason about the texture and the layouts at a different level, closer to a human being, right? In both the cases, we required a very few data points to fine tune. We are talking about of the order of a couple of hundred, maybe 1,000, and that was sufficient for TorqueAGI model to start getting to performance levels. And as we started building more and more use cases and trying out things with our customers like John Deere, we realized that the models today have really, really changed it from pattern matching from last generation CNN-like models to reasoning models. So going to other use cases, one of the questions was, hey, can we drive the tractor in the right place, right? Is it a electric pole? Is it a cement? Is it a vehicle? Is it a water creek? Now the number of exceptions just grows in a very heavy long tail basis, right? And comparing that to a different space like Waymo, in the space of self-driving car, every intersection, every open pothole, every geography is a new thing to deal with. And they started last decade. So they have to solve it by the pattern recognition way. Give it data, it looks at certain features, it solves the problem. Now, when we are working with with the new round of AI, it turns out that many of these use cases can be extracted through reasoning. You do not need 10,000 examples of water creeks to figure out it is a water creek. So that kind of a reasoning is what allows it to handle these use cases.
When you and TorqueAGI meet a new customer, what does the journey to production actually look like? What are the key milestones that you think about when going from a single robot POC to small deployment and eventually a full production fleet deployed with TorqueAGI?
When we work with customers, we tee up some of the production considerations up ahead. So number one is definition of a use case. A use case is not just that you have to perform a task, but the operational environment, the real-time considerations. Are you talking about nighttime behavior, daytime behavior? And the first question you ask is that, what is your testing setup? Are you talking about 100 samples testing, or do you already have millions of samples of testing? And from what we know, even from a public information at John Deere, they have millions of events of data that they have been testing on, right? So the testing environment, operational field thinking and thoroughness has to come first before we even start, right? But following that, the first thing we do is obviously the feasibility. And feasibility is not just, oh, the robot can do the task, but what is the leaderboard metrics on those production data points? And if that does not exist, well, let's create that and let's make sure we chase the metrics, we increase the span of data set. Once the feasibility is done, on the step two, which is the second month of the project, or usually the next 2 months to production, it's relatively seamless, because then you're talking about image sizes, deployment behaviors, test runners in the field, and so on and so forth. So we are ahead and work very closely with our customers to go from not just a proof of concept that, oh, it works, that is not important to us, but it's more that works in operational data points, and it translate on a production path as it goes to the field.
So, Ash, you mentioned a lot about how your customers are using your models and some of the use cases that they get value from. The next kind of set of questions I have are more about the brass tacks of how they actually do that. One thing that you and I have talked about is how important it is to run some of these models locally, right, on the edge, rather than doing inference in the cloud. I'm curious to hear a bit more about why that's so important for you and your customers, both from a security and performance perspective.
Being able to run on the edge is a hard requirement for most robots. So if you think about enterprise robots, they may be operating not just in a farm, but under a tree canopy where not even a Starlink can reach. And these are very high bandwidth uh, sensors that have to be responded to. So number one reason of edge processing is availability to cloud. It's not there. Whether you are in a mine, under a tree canopy in agriculture, in a construction site, inside a bridge or a dam, or in environments where it doesn't even exist, the internet. So that's why you need it. Number two reason is you have very high bandwidth and fast or low latency requirements. So you're dealing with numerous cameras, 3D sensors, large amount of data streams that have to be processed. In most of the cases, you have to return within less than 30 milliseconds or 100 milliseconds, because the robots are running in a think react loop all the time. Now, I'm not talking about low-level robot controllers that run in kilohertz, but the think react loop, which is operating at 30 or 100 milliseconds. So we have found that that's a hard requirement for our customers.
How do you think about trading off, the ambition of a truly generalist AI robot with, creating real value today? How does that inform how you develop your own product or deploy models to your end customers?
In the long run, to be able to build a general model that can do a lot of things, we need to have algorithmic and AI enhancements, and we need to collect data. We have taken a strategy that is very effective in the second part, which is collecting data. And I think the best way of collecting data is to deploy a reduced version of the AI, put it in production, because as that V1 of the model is enabling robots, that robot is now working 2 shifts a day, seeing numerous edge cases, it is learning. We use that learning the next month to create V1.1 of the model. So by the time 6 months pass, you are collected so much more data that you couldn't have collected that by paying for it. So actually, it may seem contrarian that, oh, we have to sacrifice generality by building specific AI first. From our perspective, building an AI that performs and releasing it V1 helps us iterate to build the next level of general model or general AI in a more effective manner.
Obviously, all the rage right now is, can we buy data, egocentric data, teleop data? And what you're saying is that the best way to get data is to deploy a scoped AI model and collect real world data from the real robot. That's actually the right strategy into getting enough data to build those generalist models.
And that is actually so important. And we have such a powerful tool, right? We have powerful embedding, we have transformers. So think about a manipulator, large manipulator arm handling heavy boxes of furniture and so on and so forth, right? These are boxes, large items. On the flip side, you have a bimanual a manipulator, maybe on a humanoid, doing some fine dexterous assembly, seemingly two different problems. But what we are finding again and again, not in just our model, but ablative analysis of some of the other models as well, like by Meta, whenever you're taking two entirely different problems and they are embedded into a different space, then you go deeper into the latent representations. Through the studies, you find that the concept is actually shared. Whether you are handling a screwdriver with a humanoid arm or you are handling a cylinder or a large elongated box for the other robot, they have actually very similar thinking pattern. Now they differ a lot by geometry and by perceptual data, but we should remember that this is a very powerful way of training those models.
You mentioned your data collection strategy. Previously we've talked about how Torque's belief is that even though the rest of the industry thinks you need millions and millions of hours of data to collect, you think TorqueAGI may need 1,000x less data. What is the rest of the world getting wrong about data collection, and what should they do instead?
I think I and TorqueAGI have a contrarian view to data collection. So when we were initially looking at some of the efforts going on 2017, 2015, on a lot of natural language people switching over to large models, starting with LSTMs, later on to transformer architectures, they were seeing an emergence. But emergence was based off a lot of data. They were sitting on at least 200 or 20 years of data by 10 billion people that existed as knowledge or database. And then they were able to take a decade or 5 years to build the AI, right? In physical AI, data is important. I'm not saying it's not important, but it's a wrong idea to first build the data for next 20 years equivalent. We have to find resources and methods that leverage today's data. So what exists today is good simulation, good online data sets. We should use all that. All the companies are training it on public video data sets and so on and so forth, right? That's fine. The second thing that we are doing at TorqueAGI that is unique is we're not only just relying on data that exists. We are saying, hey, physical reality has physics. It has causality. So real world models should respect the world model, the physics. And that's a very complementary value to data, which is giving us that advantage. And in fact, we are seeing that if you take a smart approach, good algorithms, good use of data, models that incorporate physics, you do not need millions of data points. And I don't think it's millions. The way some of the people are thinking about it, they're thinking it's trillions of data points. It's insane.
And so if data collection actually isn't, the biggest bottleneck, What do you think remains as the biggest bottlenecks for building and scaling generalist robot fleets today?
I think we still need substantial improvements in the models. So we are currently taking LLM, which is tokenized it flatly into a space, then taking a cosine vector. That's where we all started from. Then some people showed that the vision can be incorporated. And then VLA is like, okay, let me create some actions, right? But that's a good progression, but that does not meet the physical AI requirements at a fundamental level, right? So where what we are building, and I think some of the other people who are building and evolving, it has to go towards a newer class of models that incorporate the large scale architecture, which is very important. But it also needs to understand the robotics and physical world constraints. Now, in the video game world, diffusion models, certain 3D renderings are making it in and in closer to the model stage. So it's not just the large language model. There are tools and other things. So that movement is happening in computer graphics 3D state as well. But for robotics, something similar needs to happen. And that's where investment should go. It should go in building those models, making it work on the real robots. So we see some tractable value every 2 years for the next 10 to 10 years to make a general purpose AI.
Is there anything you no longer believe about scaling robots and building robots?
The advice I gave to every robotics and AI builder was collect a huge amount of data, uh, invest a substantial amount of your time before you release any AI model. And that was there because any AI model required redundancy. You had to give it 1,000 examples minimum of that particular situation, and combined across the situations, you're looking at 1 million data points to just get started. So that was the conventional thinking of last generation AI. So I'm no longer giving that advice. Now I'm giving the advice is collect data, but diversity and quality of data is more important. And to use that data for building testing and deployment frameworks is more important. And if you have to train the AI is actually good enough with just a few examples through fine-tuning feedback, through RL feedback, through numerous other forms of feedback. So it's an entirely new way of now building the data pipelines, which was volume-oriented, size-oriented in the past. Today, redundancy is less important, but diversity and quality is more important. Testing and few short feedback is far more important than volume-driven, AI training pipelines.
Yeah, Ash, thanks for this amazing conversation. I think me and the audience, we learned a lot about what it actually takes to deliver autonomy into production robots. To leave us off, do you have any advice you would give to founders or engineers scaling their first real fleet of robots?
Um, I think the data-driven thinking has become even more important, not less. Which means that when you're building a system, AI and statistical nature shows up everywhere. Even if you write a geometric software piece of code, when it faces the real world is variable, it's complex, right? So to build any product, we must think about testing conditions and feedback loops. The faster and shorter your feedback loops are, and this is not my thinking, this is what we have learned from leaders at YC and other people who have give product advice, it applies even more to AI model driven thinking. So data is not just for training, but it is also for creating fast testing, deployment, and model training loops.